be a little old-fashioned paper and pencil for some of the lecture notes, because I found that people can't always see the chalkboards that well in these big lecture halls. I brought like a whole army of pens, so we're going to see which one shows up best here. Our goal for today, so Friday was kind of making sure the entire class was on the same page with how to use a breadboard and connect a multimeter. And I'm also going to let me, if I zoom out like that, can those of you in the back read the text, or is that too small? Borderline? Okay. So it's kind of a discrete zoom, like I can either do this or that, there's no in between. So I'll try to make everything fit on one screen here, and if I need to like zoom out or shuffle it around, we'll go. Okay, so basically what we're going to do today is go through roughly the first half of the concept test, which you all should have done by now. I'm going to hide the results at the beginning. We're not going to do every single one of these as a poll everywhere. There's a good one in the middle where I'm going to pull up poll everywhere again. And again, thinking of this as a collaborative thing, the goal is to get everybody on the same page. So if you are confused about something, hopefully when I am going to show the results, so you will see that you are not the only one who got it wrong, so you don't have to panic that you're somehow surrounded by 100 other people who remember this stuff and you don't. And hopefully you are sitting near someone who can kind of help explain it to you, because it's hard for me to kind of run around in the middle of the lecture hall. So, very, very beginning, we're just going to quickly go through some of the basics here. In this circuit, resistors B and C are in series or parallel. Okay, you don't have to shout it out. I'll just kind of give everybody a second to think about it and then reveal the correct answer. Maybe for some of these we'll do some informal raise your hand polling sort of thing. Okay, so resistors B and C are in parallel in this circuit. Okay, but clearly there were a good, decent, maybe almost third of the class who got that wrong or mixed up. So here's the deal. Again, I'm going to try and make sure I'm writing on screen here. Series. The textbook definition of series is that the current from one element exclusively flows into the next element. Okay, so another way to think about that is things are sort of connected end to end, or only at one end, right? So current is the same in series, however you remember learning that rule from physics. So resistors B and C are not in series there because there's a junction here. We'll talk about that more later. So if you looked at those and thought like, oh, maybe in theory, if there was current, if I can get the lid off this pen, if you looked at that and thought, well, what if there's current, does the red show up okay? Yeah, the red kind of shows up okay. What if there's current going that way that aren't B and C in series? No, the current is not exclusively flowing from B to C, right? So they're not in series. They are in parallel, which means that they are connected at both terminals or both ends. And this is where you guys are going to start to get introduced to my lousy handwriting. Let me know, because I'm going to be looking down here, so if it's ever off screen, kind of let me know if I need to slide the paper around. It is important, maybe one of the things that trips people up here, electrically in parallel does not mean geometrically parallel, right? So this is drawn differently, but drawing that like this, these two circuits here are electrically, I don't know if I actually close and connect that line, these are electrically equivalent, okay? If you trace the path that the current flows through each one of these, it's going to split, go through each resistor, and then join again at that bottom node. Okay, so even though the physical layout is different, and again, there was a question about this later, it doesn't matter how I draw this one, right? I can do that. That's still parallel, okay? The shape of the wire doesn't matter. It's just those wires just represent zero resistance connections. So the shape of the wire and the physical angle of the resistor symbol on paper have nothing to do with whether it's electrically in series or parallel. Same thing for series. I can do, I don't know, this, draw a line up there, and do that. Right? So geometrically, those two squiggles are next to and parallel to each other, but electrically they're in series. Okay, so basic concept, kind of fundamental to a lot of the stuff that's going to follow when we start talking about voltages and currents. So I guess any questions or clarifications, and again, don't be ashamed because there are like a few dozen other people who got this wrong. So questions or clarifications about series or parallel? Yes?
So are the pair of resistors B and C in series with resistor A?
Yes, so the question was, are the pair of resistors B and C in series with resistor A? Yes, if you kind of draw a box around what we call this branch of the circuit. The branch, so there are kind of two, there's an entry and exit point to this branch of the circuit, right? That combination of resistors is in series with resistor A. But individually, B is not really in series or parallel with A, right? It's just the combination, and some of the further questions are going to talk about equivalent resistor values in series or parallel. If you imagine, so getting a bit ahead, if you imagine lumping this into a single equivalent resistance, say BC, that would be the same as saying, I'm going to try and squeeze this in here, resistor A is in series with resistor BC, where BC is the equivalent resistance of B and C combined in parallel. Okay? Any other questions about the series parallel stuff? Okay. I am gonna have to like move this off camera each time and then hide the results again. Okay. Which branch or section of the circuit has the least resistance between its endpoints? Okay, let's do, let me check the results first here. You're not gonna fall on this one. Okay, so if you measure the resistance from one endpoint to another, which one has the least? This one, and people were generally better with, but still a few dozen people who got this incorrect. So basic rule here is when you combine resistors, and here we are doing this with a circuit schematic representation. On Friday we were doing it on a breadboard in Tinkercad. In series, the resistor values add, so the equivalent, I didn't give these subscripts, but if this was R1 and this was R2, is R1 plus R2, and if I added more of these in a chain, it would be plus R3, and so on. So think of these like you have to be careful with the water analogy, but sometimes it's helpful. If you imagine these, each resistor is kind of a section of a pipe with maybe some obstruction in it that water has to flow through. If you keep chaining those pipes together with more and more instructions, that resistance is going to add. It's going to become harder for water to flow through it, right? In parallel, oops, smell, the resistances add inversely, which means if you keep adding more things in parallel, the resistance actually goes down. And again, think of it like adding pipes. If you keep adding more pipe segments in parallel, right, you're making it easier for water to flow because there's kind of more paths it can take. So the equation for that, which again, hopefully you remember from physics, 1 over the equivalent resistance is 1 over R1 plus 1 over R2, and then if you added an R3, and so on. So again, think of if I added R1, R2, R3, and so on, I can keep adding things in parallel, and I think the counterintuitive thing there is first you glance, you go, there's more resistors, so there must be more resistance. Again, you're giving more paths for the current to flow, so you are making it easier for current to flow from there to there, okay? And this is relevant not just in physics homework problems, but when you get your resistor kit, I think I mentioned this last week, resistors only come in certain discrete values. I see your hand, I'll get the question in 1 second. So you might need a 150 ohm resistor, but you only have 100 ohm resistors in your kit or something, right? So you can use these equations to combine multiple resistors to get the resistance value you want. Question?
Don't you have to take the reciprocal of the entire?
If you are solving for REQ, so this is written as 1 over REQ equals 1 over blah, blah, blah. So if you want to solve it for REQ, then it's 1 over R1 plus 1 over R2, the whole thing, the minus 1.
I didn't see that, sorry.
Okay. Yep, so, and I will be, if you can't see my lousy handwriting or don't get something before I flip to the next page, I will be scanning and uploading these as a PDF to Canvas later. But yes, there's a 1 over REQ there. Okay. Questions about resistors in series or parallel? Good? Okay. All right. This one I think we are going to do as kind of an informal show of hands vote because it was kind of a even distribution. So circuit 1, we've got a battery and a single resistor. Circuit 2, we have added a second resistor, but we have the same battery in both resistors. This is all symbolic, there's no numbers. Just say battery is voltage V, I'll write that on there. and the resistor's resistance R. How does the power dissipated by resistor A change when resistor B is added? Okay, so the options are going to be increases, decreases, or stays the same. Think about it for a second, and then we're just kind of going to do an informal show of hands poll. Okay, I'll give you 10 seconds to think about it. Okay. Who thinks the power dissipated by resistor A increases? Grab resistor 2. Okay. Who thinks it decreases? Who thinks it stays the same? Okay, so it looks like maybe people looked at the results. I forget, did it publish the results? Did it show you the correct answers after you did the concept test? I forget if I had it set to like wait a certain number of hours or something to show those. But I think you should be able to go on if you want to check afterwards. Again, this will be in the notes too. Okay, the correct answer is that it decreases. So kind of quickly remembering some equations from physics again, you have the power dissipated by a resistor is equal to IV, so current times voltage. You can also use Ohm's law, which we didn't actually write down yet. So Ohm's law, if you remember one thing from physics, hopefully it's Ohm's law, V equals IR. So you can also write power as I squared R or V squared over R by substituting in Ohm's law. From Ohm's law, if I add a second resistor here, right, resistance has gone up, voltage has stayed the same, so current must go down, right? And then if I look at, I'm going to try if the highlighter shows up here at all, the power dissipated by a single resistor, okay, that showed up. If the resistance stays the same and current goes down, power must also go down, right? So I think some of the people who said stays the same, you look like, oh, well, the resistor value didn't change, so the power dissipated by it must stay the same. The current going through that resistor went down, so the power dissipated by it also went down. Okay, and again, you can see a lot of people kind of, does that, if for anybody who originally voted stays the same there, does that kind of clear up that misconception, or do you have another question about it? Is that a hand in the back? No. We good? Again, like a third of the, almost as many people got this wrong as got it right, so there's kind of no shame in like asking to clear stuff up at this point. We good? Everybody's just frozen in fear? Can't tell? Okay. Let's try. And again, I don't, the last time I taught this class, it was Tuesday, Thursday, so I'm still recalibrating myself for the 50-minute lectures. So don't get used to getting out early. If we get through all of these today, I'm going to kind of keep going with stuff that I would have saved for Wednesday otherwise, so we'll see. Okay, here is another one that people had a lot of trouble with, so we are going to do another vote by hand if the document cam decides to focus. Hello? There we go. In which circuit or circuits does the resistor dissipate the least power? Okay, so circuit 1, we got a single battery. Circuit 2, we have an additional battery connected in parallel. And in circuit 3, we have an additional battery connected in series. In which of these circuits does the resistor dissipate the least power? Think about that one for a minute. Talk to the people next to you if you're not sure, and then we'll kind of do it. I don't have this one set up as a poll. We'll do another just informal vote. And note the circuit or circuits there, the little S in parentheses, so you could pick more than one circuit for the least power. All right. How many think circuit 1 and only circuit 1 dissipates the least power? Okay, don't be shy. Just commit to the vote. Be proud of it. Come on. Okay. Circuit 2 and only circuit 2 dissipates the least power. Okay. No votes for just circuit 2. Circuit 3 and only circuit 3. Okay. Circuits 1 and 2 both dissipate the least power. Okay. How about circuits 1 and 3? 2, and 3. All 3 of them are the same. Okay, so it looks like the people who had this right hopefully help convince your neighbors. The correct answer here, although again on the original concept test, a lot of people got this wrong. The correct answer is circuits 1 and 2. I think the original misconception people have here is you look at this one and go, oh, there's 2 batteries, that must be more power, right? So that's why you saw a lot of people picked just circuit 1 or said, I don't know. But if let me pick a color here. Okay, let me ask, what is the voltage across the resistor in this circuit? Shout it out. The battery voltage is just V. V, right? If I add another battery in parallel, what is the voltage across the resistor in this circuit? Still V. Okay, power dissipated by a resistor. P equals IV or V squared over R. Even though there's another battery here, oops, voltage hasn't changed, resistance hasn't changed, power dissipated by that resistor has not changed. Okay, what has changed here by adding more batteries in parallel, these 2 batteries will last twice as long. Okay, I am now drawing half the current from each battery. So in this circuit, if we call the current I, over here, I'm still going to have I through the resistor, but I'm only going to be drawing, sorry, that's getting a little tiny and messy, but 1/2 I out of each battery. So adding more batteries in parallel basically extends your battery life. And if you look at just common batteries, right, like AAA, AA, C, D batteries, they're all the same voltage. If you get out a multimeter and measure a fresh alkaline battery, it's about 1.5 volts. So the bigger battery doesn't get you more voltage, but bigger batteries have more capacity. They will last longer. Okay, so or same for little coin cell watch battery sort of things. They're actually 3 volts, but they are designed for low current applications. So you wouldn't use those to power motors or something. So you aren't really going to have to purchase batteries in this class. You're going to be given the batteries in the kit for your robot, but I guess something to consider in the future about kind of if you need a battery to last longer, then you either need a bigger battery or more batteries in parallel, as opposed to this case where we've added 2 batteries in series. Right? Voltages add in series, so in this case the voltage drop across the resistor is 2V, and now the power dissipated by the resistor in this case is higher. Okay, so again, just kind of getting over that intuitive, like, oh, there's more batteries, there must be more power trick there, that the voltage across the resistor hasn't actually changed. Okay? Questions on that one? Yes?
Is the second one equivalent to like a half voltage battery?
The circuit 2?
Yeah.
No. So these batteries, the question was, is the second one equivalent to a half voltage battery? If the third one, if each one of these was 1/2 V, then that would be equivalent to this, right? Because voltages add when you connect elements in series, right? So 1/2 V plus 1/2 V in series is equal to 1 V. If each one of these was 1/2 V, then those voltages are equal in parallel, so the voltage across the resistor would still only be 1/2 V. Let me kind of write that down over here. So voltages add in series, right? So if I connect a bunch of batteries in series like this, and so call that V1, V2, V3, then V total across all of those is V1 plus V2 plus V3. And voltages are the same in parallel. So if I connect, well, let me say that, voltages should be the same in parallel. So if you want to connect a bunch of batteries in parallel, like this, V1, V2, V3, you need to make sure they are all the same type of battery with the same voltage. Because sometimes people ask, okay, well, what happens if I connect a 9-volt battery in parallel with a 1.5-volt battery? And the answer is bad things. Because you now have effectively a 0 resistance path between two, 0 in kind of the perfect physics homework problem sense. In the real world, there's a little bit of resistance in the battery contacts and the wires used to connect them and things, but in Ohm's law, you have a fixed voltage difference here. Resistance is almost 0. That means current approaches infinity, which in real life gives you a short circuit that melts things. Okay? Does that answer your question?
Yeah, I'm just wondering like why the second one decided the adder of the battery only does feel like half of the current.
Why does it only do half the current?
Yeah.
Because, so Kirchhoff, the question is why does it only do half of the current? So the voltage, the current through this resistor is determined by Ohm's law, right? So V equals IR, I equals V over R. That is always true regardless of where this voltage source is coming from, right? I can put as many batteries as I want in parallel here, as long as they are all the same voltage. The voltage across this resistor doesn't change and this current doesn't change. There's no way for the batteries to force more current through the resistor. So if I originally had I, so for the sake of to make the math easy, say it was just 1 amp, right, going through the resistor, and I add a second battery, the two batteries combined cannot force 2 amps through the resistor. So that's not how Ohm's law works, right? So say it was just 1 volt, 1 ohm, and 1 amp, just to make the math easy, right? I had a second 1 volt battery in parallel. Ohm's law still says I get 1 amp through the resistor, which means at this junction, according to Kirchhoff's current law, so which you should have learned in physics, currents are the same in series when you have 2 elements in series, right? But again, think of it like water flow. If I have a junction in a pipe, then the mass flow rate has to be conserved, right? So if the current splits, then I'm going to have, say, 1 amp there, and 1/2 amp there, and 1/2 amp there. Same thing here, I have, in this case I drew 3 batteries, so I would have 1 amp here, and 1/3 of an amp coming from each battery, adding up to the 1 amp. The current has to be conserved. Does that make sense? Okay. Okay. Again, sorry, I'm trying to kind of scroll around here to make that all fit. Any other questions on this one or any of kind of the others? Again, this in theory should all be reviewed from physics, but this is the point of this test to kind of catch stuff that people don't remember. Yes?
How did you reason about the batteries in parallel where the voltage is the same? How
Here? So I've been, Kirchhoff's voltage law and Kirchhoff's current law are the 2 formal ways of saying that voltages are the same. So if I have 2 resistors connected in parallel, right, then I know the voltage drop across them has to be equal, right? In the physical real world, I would have the choice to take multiple batteries of different voltages and connect them in parallel, but voltages want to be the same in parallel, for lack of a better phrase. So if you intentionally connect 2 things with different voltages in parallel, now I have a voltage drop of 9 volts here to 1.5 volts here. And if I look at Ohm's law, so I have a fixed non-zero voltage drop at almost 0 resistance, so I'm going to have almost infinite current. If I solve for the current, I equals V over R, where in this case, say V is 7.5 volts and R is almost 0. So the current's going to be huge, and that's going to cause things to heat up and melt, basically. Was that what you were asking, or were you asking about this reasoning for why the voltages should be the same?
Oh, so there's like, for the 9 volts, is that going up? Like going up to the other side?
Yeah, so current would be, in this case, flowing from the higher voltage to the lower voltage. And we'll talk about this with the passive sign convention a little later in lecture today.
Yeah, that's good.
Okay, yeah, so it is, I mean, this is how, so with resistance in there, so you don't get infinite current, that's a very simplified way of explaining how battery charging works, right? Like you plug your phone or your laptop or whatever in, current is flowing from a power supply into another battery. You just would not want to, literally later in the semester you'll get a kit with a 9 volt battery and 1.5 volt batteries. You don't want to short circuit those 2 voltages together because of this. If there's no resistance, then very high current will flow. So this is fine if V1 equals V2 equals V3, because then all of those voltages are equal and it's okay. It'll draw equally from each battery. Okay? Okay. Other questions on kind of the batteries in series and parallel, or any of the other half a dozen different topics that came up there? Good? Okay. Next. This is a similar one to, I think, 2 questions ago, so we're going to go through this kind of quickly. I don't think we're going to bother with the voting poll. How does the resistance between the endpoints of the branch change when the switch is closed? So when this switch is open, it's kind of like this resistor isn't here. Current can't flow through that path, so we only have current that can flow this way. So the total resistance there, those 2 resistors are in series, is going to be 2R. If I close that switch, right, now these 2 resistors are in parallel, so their combined equivalent resistance goes down. Remember, when you add resistors in parallel, resistance decreases. So the total resistance from one endpoint to the next is going to decrease. And even though there's, if you look at it, they go, the switch closed, there's another resistor, more resistors means resistance must have gone up. That's not the case when you're adding more in parallel. When you add more in parallel, resistance goes down. Okay. So again, that was similar to kind of 2 questions ago. So questions on this one? I guess the point here is that you can also, we've been talking about pairs of resistors either just in series or just in parallel. You can make more complex resistor networks to get a single equivalent resistance, which again is one thing in lab where you need a specific resistance value and you might have to use 2 or 3 to get the value you need. In the real world, if you're designing a device for production, that's going to get more expensive, right? The more parts, it's going to take up more physical space on a circuit board, so maybe a little more unlikely to actually do that as opposed to finding a single resistor or kind of redesigning other things in the circuit to be as closer to a single value. But again, when you're doing this in lab, kind of practicing, or in the homework assignments, you can, you look in your kit, you go, oh, I don't have a 125 ohm resistor or whatever I need. You can make one. Okay. Let me check the next one. All right. This goes back to what we were talking about a few slides ago about the physical layout of things. So which of these 3 circuits are equivalent? And again, for the sake of time, because I want to make sure we get to the poll everywhere discussion one that's going to take a little longer, I will cheat and tell you now, these are all the same electrically, even though the physical layout is completely different. Okay, so however it helps you to kind of visualize or trace, these 2 resistors are in parallel because they are connected at end to end and connected to the battery there, so current flows out the battery through that resistor, through this resistor, back to the negative terminal of the battery. Same thing here, okay? Even though I have moved one resistor physically over to the left side, the electrical connection didn't change. Okay, both connected to the positive terminal of the battery there and the negative terminal of the battery there. And then same thing over here, all I did was rotate the resistors 90 degrees, but the point-to-point wire connections did not change. Okay, so this is important to understand. So again, the correct answer here is that all of them are equivalent, but it looks like on that left-right switch is kind of what tripped people up on the concept test. The second most popular answer here was only circuits 2 and 3 are equivalent. Usually in textbooks and lab diagrams and stuff, the convention is kind of to draw the battery on the left, so the way it's drawn in 2 and 3 there is just kind of weird. But that can throw you off, right? Like every once in a while you may encounter one that is mirrored or something is rotated for whatever reason, and if it's not equivalent to the exact version you initially are used to seeing in the notes of the textbook, you'll think, oh, that's something completely different. But again, what matters is the point-to-point electrical connections and not the geometric arrangement. Okay. All right. This one, I am just going to not even bother hiding the answer first because it's basically just the inverse of the one we saw previously. Just asking which one's dissipating the most power instead of which ones are dissipating the least power, but otherwise it's the exact same diagrams. Again, I'm not going to bother writing on this one, or I'll do it real quick. We have 2 batteries, V in series, so you get 2 volts over that resistor, and the power dissipation is going to be higher than the other 2. Okay, but again, that's just asking the opposite of the first question, which is sort of a trick in survey design to make sure people aren't just going through and clicking A on everything, right? Like if you were answering these questions honestly, then you got the other one right, you should in theory also get this one right. Again, since there was an I don't know option and this isn't graded for correctness, hopefully everybody took it seriously and didn't just go through and click the first option on me. Okay. Next up, oh, when are we going to get to the good one? Okay, this is another good, important misconception one that most people got right, but not everybody. So the current through point 2 in the circuit is lower, higher, or the same as point 1. For the options, the correct answer was that it is the same. So this is, again, I think somebody did ask about this lecture after lecture last time. Current does not get used up or dissipate as it goes through a circuit, right? So when elements are in series, the current, and this is where we talked about this with the multimeter measurements last time, if I wanted to hook up a multimeter to measure current in this circuit, I could put it there, draw my little A, or I could put it there, I would get the same reading. Again, if you think of this as water flowing in a closed loop with a pump, right? So a completely closed system, there's no water leaking out or anything, right? So as long as it's in series, current's the same, current is not somehow lower at point 2, okay? This one had a split, so I think we'll do a quick informal vote on this one. And I have 2 resistors connected in parallel to a battery. What happens to the voltage difference between points 1 and 2 if resistor B is removed? So if I get rid of this, what happens to the voltage difference between points 1 and 2? Does it increase? Does it decrease? Does it stay the same? Yes, okay. Correct answer. Again, a lot of people, again, I think maybe having kind of a misconception about like, oh, you removed one of the resistors, so resistor A is getting more voltage or more power from the battery or something. Not the case because they are in parallel, right? If this is voltage V, then it doesn't matter how many resistors I add or remove in parallel here, the voltage across all of them is V, okay? And assuming an ideal battery that can provide infinite current, which is not the case, we'll talk about that, I don't know if we're going to get to it today, but maybe next time, that also actually doesn't change the current through either one of the resistors, right? So Ohm's law applies to these individually, V equals IR, so as long as the voltage across it is V, the current through each one is just going to be fine. Again, plug in ones for everything, call it 1 amp or whatever. But clearly in the real world, that's not true, right? You can't get infinite power out of a single AA battery. So mathematically, if you have a perfect voltage source, that's true. We'll talk about non-ideal voltage sources hopefully next time. Okay, questions on that? Okay. All right, this one, we're going to take a minute because I think this is something that people usually actually don't see in physics, the use of the ground symbol. So this one usually trips people up. We have 2 batteries in series connected to a resistor with this funny looking ground symbol here, right? In this circuit, it's connected directly to point 2. In that circuit, it's connected between the 2 batteries. Okay, so the question was, the voltage difference between points 1 and 2 is, I forget what the answer's out here. Greater in circuit A, greater in circuit B, the same in both circuits. I have no idea. Okay, so I have no idea, got the most enthusiastic votes there. Forget about voltage completely for a second. We're going to talk about elevation as an analogy. Okay, so forget about electricity. We're going back to mechanical territory. Here is my little stick figure drawing of a mountain and the beach and the bottom of the ocean, right? And there's a little person standing next to the beach. Okay, and let's say that the top of this mountain is at an elevation of 10,000 feet relative to sea level, right? And the bottom of the ocean is 1,000 feet below sea level, right? So if I ask you, what is the elevation of Ithaca, New York, or your hometown, or whatever, it is implied that I mean relative to sea level. Okay? We have a defined 0 reference, but elevation is defined between 2 heights. It's just we usually have it like If I ask you like how tall am I, right? It's implied that I mean relative to the floor. I'm not like measuring from my waist or some other, or the ceiling or some other arbitrary point. But I could do that if I wanted to, right? So I could say, okay, in this scenario, the distance between the bottom of the ocean and the top of the mountain is 11,000 feet. If, whatever, the ice caps melt and the ocean level floods everybody and goes up by another 1,000 feet, then my zero level has changed. Okay, now the top of the mountain is only 9,000 feet above sea level, and the bottom of the ocean, if I'm measuring relative to this at zero, is at negative 2,000 feet. But the distance between the top of the mountain and the bottom of the ocean hasn't changed. Right? It's just sea level, or what I have defined as zero. So does that physical analogy make sense for everybody? Again, distance is measured between 2 points. Okay, if you're doing a dynamics problem and you have your XY coordinate system, it's relative to the origin, but you could measure distance relative to x equals 3 if you wanted to, or whatever. Okay? Exact same thing with voltage. Voltage is measured between 2 points. That ground symbol is just where we define zero. Okay, so in this problem, I have voltage drop V across this battery, V across this battery. So the voltage drop across the resistor is 2V, because the batteries are in series. Same thing here. Even though I have moved my zero, I'm calling that 0 volts, the difference between this point and this point is still 2V. Okay, if I asked you, what is the voltage of point 1 relative to ground, then it is different in those two circuits. Okay, so in this circuit, 1 relative to ground is 2V, and 2 is at ground, so it's just 0. In this circuit, relative to ground, point 1 is at positive V. In this circuit, relative to ground, point 2 is at negative V. Okay, but the difference between 1 and 2 is still the same. Again, that's the same as, hopefully the sea level analogy relative to sea level makes sense there. If the circuit 1 over here on the left would kind of be like if the ocean drained completely, and I was just measuring relative to the ocean floor. Circuit 2 over on the right is the ocean is somewhere between the ocean floor and the top of the mountain. Okay? That is what this means mathematically. Physically, when we talk about building wiring, there is literally an earth ground somewhere, right? That is kind of the origin of this symbol. There's physically like a copper pipe or a big piece of metal or something in the ground to kind of help absorb or discharge. You know, then you're getting into talking about lightning strikes and surges and all of that stuff. You're not really worried about that when building a robot, right? Like your robot does not physically have an external earth ground. So technically, you might see a chassis ground symbol instead that looks like that instead of like this. From what I've seen, I think every physics or electronics textbook I've ever seen uses this symbol anyway. But technically for a battery-powered circuit that isn't plugged into the wall, it's not an earth ground. But again, for purposes of this course, using that symbol is fine. And again, most people, a lot of people just said, I don't know on this one. I'm assuming because you didn't see a lot of that ground symbol in physics. Is that right? Okay. Okay. This is important going forward to kind of have that misconception cleared up. So any questions about the ground thing? Okay, we got about 10 minutes left. I'm going to make sure we get to the pull everywhere one, and then we will do. I need to make sure I talk about passive sign convention too, so you guys have that for homework one. So I might skip. Okay, good. The next one is the pull everywhere one, but I am going to do passive sign convention real quick because you need that for homework one, and then we'll do the pull everywhere question to wrap up. So just like how in dynamics, right, you have, say, an XY coordinate system, and you might define positive X is to the right and positive Y is up, and you have some mass with velocity V. If you do whatever the dynamics problem is and get a negative number for velocity, then you know it was actually going the other way, right? Same thing here. In electronics, we have what's called the passive sign convention, where you are probably used to seeing plus and minus signs on a battery, but probably not plus and minus symbols on a resistor. Somebody actually asked about this last time. Well, can you flip, you talked about the LED can't be backwards, well, can the resistor be backwards? Can you flip the resistor around on the breadboard? Physically, yes, resistors do not have polarity, but when doing circuit analysis problems, we define, and when I say define, I mean this is a definition, just like you define which way positive X is. That positive current I flows out of the positive terminal of a source. So if you have your battery there, battery is a positive and negative terminal, and into the negative terminal of, into the positive terminal of a passive element like a resistor. So when you see homework that says label passive sign convention and current directions on all of the components in a circuit, that's what this means. For a simple circuit like this with just two parts, that seems obvious, right? But for, say, something more complex, like what you might see later in the semester on homework or prelim or something, say I have, this is called a bridge configuration, a more complicated resistor network with 5 resistors like this. Come on, document cam, focus for me. Sorry, autofocus button. There we go. So I can look at that and say, okay, I'm going to put signs on all my resistors like this because it seems kind of obvious that current should be flowing from top to bottom through those, but depending on the resistor values, I don't really know if current's flowing left or right through that middle one, right? So I'm just going to pick, flip coin, doesn't matter, positive and negative there, and then, okay, we'll talk about this more in the coming lectures. If I solve for that current and get a negative number, then I just know it's going the other way, right? Exactly like defining your X and Y axes and which way is positive. So that's all this means, okay? It is to help keep track, because if you don't do this and you solve this and get a number, I get 2.3 amps for that, but I don't have sign conventions defined, then I don't actually know which way it's going, okay? So, and that, homework 1 asked about this, it'll matter a little more in homework 2. There's also a video in the circuit theory playlist on Canvas that goes over that. So I don't want to spend a ton more time on it now because I want to get to our final poll everywhere question in the last few minutes. If my mouse decides to work. There we go. Okay, I am going to activate this question. So it should be on poll everywhere, but I'm going to stick with the document cam to show it here. What is the voltage difference between points 1 and 2 in this circuit? Okay, your options should be 0 volts, 6 volts, 12 volts, and I don't know. Yes?
Is this assuming the switch gets closed? Is it like that?
No, it's in this state where the switch is open. So not like after the switch closes or anything. What is the voltage difference between points 1 and 2 in this circuit? 12-volt battery, 2 resistors with value R, and the switch is open. Okay, we got 72, 73 votes in. I want to make sure I have time to explain this, so try to get your vote in quickly. Okay. Responses. All right, well, we're almost evenly split. All right, in the next minute or two, convince other people why you're right and revote. We're like 50-50 split. Who's right? I think it's set so you can change your vote. Maybe we're edging towards A. C is not fluctuating.
If I were to connect the points 1 and 2, oh wait, maybe certain like that. You are wrong.
Okay, we're whittling away at C. Some people are holding on to it. Nobody with B anymore. Okay, I want to make sure I have time to explain this, so I am going to deactivate, but again, this is still just for participation at this point, so don't worry if you got it wrong. All right, last chance, 5, 4, 3, 2, 1. A, 0 volts, is wrong. So, for those of you who stuck with C, that is funny. That is I did the same thing the last time I taught, and like the one girl who hung on to C was like, yes, when I announced the answer. So 0 volts is incorrect. Here's why. Let me switch back to the document camera. So, forget this circuit with 2 resistors for a second. If I draw a single circuit with just a battery, a 12-volt battery, what's the voltage across that battery? 12 volts, right? If I add an open switch here, okay? The resistor's not there yet. What is the voltage across that open switch? 12 volts, right? If I add a resistor here, I have an open switch. What is the current through this circuit? 0. Ohm's law, V equals IR. The current through that resistor is 0. What is the voltage drop across that resistor? 0. If the voltage, so again, let's talk about ground. If I define a ground symbol there, I didn't have a drum, but if this is 0 volts, what's the voltage relative to ground here?
I see.
12.
Nothing going through.
If the voltage drop across this resistor is 0, what is the voltage there? 12. So what is the voltage drop across the switch, even though the resistor is there? 12? People believe me about the 12? Does that change if I had another resistor here, like in the original problem? No. Current through that resistor is 0. Voltage drop across that resistor is 0. Voltage here relative to ground is 0. Voltage drop across the switch is 12. Correct answer was C. So, congratulations for those of you who stuck with that. We are out of time. We will pick up with the rest of these on Wednesday. Thank you.